I hope everyone's having a great morning. I am Mr. Ish. Thank you for joining me. We have to evaluate that definite integral sine x plus cosine x from 0 to pi, and I've already given you the value, it's 2. The antiderivative of that minus cosine x plus sine x from 0 to pi is easy to evaluate and you'll get a 2. But our task is to evaluate by means of Taylor series centered around a equals 1. And you have the Taylor series expansion template over there. The ordered derivatives with the a coming in times x minus a to the power of n divided by n factorial. In all instances, a is equal to 1, and you need your calculator for this. It will be slightly complex. Let's bring out the ordered derivatives going up to n equals 4 for sine and cosine. When you're looking at sine, the zero order derivative is just basically sine x, a equals 1, so that's what it is. The zero order, then the first order will obviously be cosine of 1, then you'll have a minus sine of 1, then a minus cosine of 1, and then finally you'll end up at sine of 1. These are my 0, first, second, third, and fourth order derivatives of sine x. That's what it is. When you're looking here at cosine, obviously in all of these areas where x is, you're bringing in a equals 1, hence you're seeing these 1's come through. The zero order derivative is obviously cosine, but we're bringing in a 1 because a is equal to 1, as you see. And then you know you're going to go from here, minus sine of 1, then minus cosine of 1. There's no point in computing any of these right now, it's too early. Then from here you'll have a sine of 1, then finally you'll have a cosine of 1. That's what it is. Now all of these will come into your expansion formula, and each of these represents the part right over here. So how is everything going to play out? It's going to play out like this. Let's do the sine, and then we'll do the cosine, and we'll add them up. The sine ones will be the sine 1, and then you'll look right over here, x minus 1 to the power of 0 over 0 factorial plus cosine of 1. You're coming here, x minus 1 to the power of 1 divided by 1 factorial minus, you see this minus, don't forget that, sine of 1, then x minus 1 to the power of 2 divided by 2 factorial minus right here cosine of 1, x minus 1 to the power of 3 divided by 3 factorial. We're only going up to 4 plus sine of 1 times x minus 1 to the power of 4 divided by 4 factorial. That's coming here from the series expansion of sine x, which is this part right over here. Now let's look at this part, and that will be, and you'll still put a plus over here because it's a plus right over here. I'm again going only up to n equals 4. Obviously the smaller that n value, the less accurate your definite integral outcome, but still close enough. Let's bring in these. You'll have cosine of 1, then x minus 1 to the power of 0 over 0 factorial minus sine of 1, then x minus 1 to the power of 1 over 1 factorial minus cosine of 1 times x minus 1 square over 2 factorial. Then we write here plus sine of 1, then x minus 1 to the power of 3 over 3 factorial plus right here cosine of 1 times x minus 1 to the power of 4 over 4 factorial, and we'll stop right over there. All of this is being integrated from 0 to pi, and then you can see here dx. That right there is everything. When you simplify this, x minus 1 to the power of 0 is just a 1, 0 factorial is just 1. All of this will boil down to just a sine 1, which is fine. There's nothing wrong with us simplifying right here. Cosine 1 times all of this is just equal to just cosine 1. 0 factorial and anything to the power of 0 is always a 1. X minus 1 to the power of 1, we can keep that, but this right here is a 1. This here is just a 1. Right here, 2 factorial is a 2, 2 factorial is a 2, 3 factorial is a 6. All of this will come into handy calculation later on. This here is a 6, this here is 4 factorial, a 24, so let's bring a 24, and this is what we have. For simplification, we'll do everything here in terms of the antiderivative in pairs, and it's easy because there's a lot of repetition coming into play. All of these cosines and sines are all basically constants, and look, don't lose sight of your positives and minus, but what I'm putting a square around are basically all of my pairs, which will have very similar antiderivatives. We will do u substitution here, polynomial substitution, because trust me, it works very well and it's easy. We will post the numerical outcomes over here. When you're doing the antiderivative of sine 1 and cosine 1, you're really looking at just basically sine 1 dx, or you're looking at cosine 1 dx. This can come out. You really have just basically sine 1 times x, and you're looking at it from pi 0. From all of this, you're going to get something which looks like that. So essentially, what you will be doing here is sine 1 times pi. You'll keep your calculator here on the RAD mode and just do 1 sine and multiply it by 3.14, which is pi. From this item right here, we're getting here a 2.643. Now let's evaluate here. Cosine 1, it's always obviously a positive, and again here it's just going to be basically cosine 1, and then x will be the antiderivative coming out from here. You'll do 1 cosine times pi. You have 1.697 coming from right here, and let's put that down here. We're doing the definite integration of each of these specific items. Now we'll come over here. You're going to do u substitution. If u is equal to x minus 1, du is equal to dx, then u1 and u2 are equal to, based on this, you have obviously 0 and a pi. That's what you have. X minus 1 is a 0 minus 1, which is a minus 1. X minus 1 with a pi is a pi minus 1. Your integral becomes this, minus 1 to pi minus 1. I'm looking right over here. Cosine 1 can be pushed outside. This over 1 is meaningless. And then you have a u du. You know, from here you're getting a u square over 2 as an antiderivative cosine 1. And then you have a pi minus 1 and a minus 1. That's all what's coming out from right here in terms of its antiderivative. Keep your calculator on the RAD mode. Now we'll do the lower limit and the upper limit, and then we'll multiply here by cosine 1. We'll do a negative 1 square divided by 2. Then I'll do pi minus 1 square divided by 2, minus that from my lower limit evaluation, and multiply this by 1 cosine or cosine 1 in RAD mode. I'm getting a 0.9688. This 0.9688 is coming from right here, 0.9688. Now we have a minus, we'll put a minus. The only thing which changes between here and here is nothing other than your coefficient. Everything else stays the same, because these variable parts of these power series terms are the only things which are serving as the integrands. These cosine and sine components are serving as constants, and that's the only thing which changes. Everything after that with regards to the variable components is the only thing which is being integrated. You're going to integrate this, but exactly what you see here, minus 1 square divided by 2, and then that from it. So let's do pi minus 1, we'll square it, divided by 2. I already have the previous saved value for the lower limit. I'll multiply this by sine 1 on the RAD mode, and I'm getting 1.508. Let's put that here, 1.5089. We've done all of these. Now we have 1, 2, 3, 4, 5, 6 more to evaluate. And we don't have to repeat our procedures here too much, and I'll show you why. These things will always stay the same. These exponents here will stay with the u integrand. Look, minus 1, pi minus 1. I have a x minus 1 square. If u is x minus 1, this is a u square du. That's exactly what it is. I have a 1 over 2 sitting out. I'm doing here a u cube over 3 with a 1 over 2 sitting out. Pi minus 1 and minus 1, and the only thing which will change over here is either a minus sine 1 or a minus cosine 1, and that'll be easy. So let's evaluate that. Put your calculator back on the RAD mode. Let's put minus 1 first. We'll do a minus 1 exponent 3 divided by 3. I'm going to save this value. Now we'll do pi minus 1. Pi minus 1 exponent 3 divided by 3 minus that lower limit outcome multiplied by 0.5, 1 over 2, multiplied by this sine 1. I'm getting here a 1.5177, but there's a minus, so we'll put here a minus 1.5177. Now we'll do this cosine, but everything is still the same. You're just multiplying by cosine 1. That's all what it is. Do a pi minus 1 exponent 3 divided by 3 minus the lower limit outcome divided by 2, because there's a 1 over 2 sitting outside coming from the factorial, times cosine 1 on the RAD mode, and you're getting 0.9745. And I'm going to put that right over here, minus 0.9745. Now we're coming over here. Nothing will change over here other than the fact that we have here a u cube, and this thing will become a u to the 4 over 4. And you're seeing nothing is changing beyond that, and the factorial, here you're going to have a 1 over 6. You'll still have a cosine 1 and a sine 1 based on their signs come through, so it's not too bad. You're going to put a minus 1 first. It's a minus 1 to the power of 4 divided by 4, 0.25. We'll save this. Now we'll do pi minus 1 exponent 4 divided by 4 minus that lower limit outcome divided by 6, which is your factorial component, times, I'm right over here, cosine of 1 on the RAD mode, and I'm getting 0.451. I'm getting a minus 0.451. We'll do the exact same procedure here with a positive sine 1. Everything else stays the same. We have a pi minus 1 exponent 4 divided by 4 minus the lower component divided by 6 times sine of 1 on the RAD mode, 0.702. plus 0.702. Now we write over here, what will change? This will become to the power of 4. This here will become, in terms of the antiderivative, 5 over 5. This here will become over 24 because, as you see, the factorial gave us a 24. We're still going to evaluate with the sine 1 and the cosine 1, but they're all positive. Put your calculator back on the RAD mode. Let's look at this. We'll do a minus 1 exponent 5 divided by 5. I'm going to save this value. Now we'll do pi minus 1 exponent 5 divided by 5 minus that saved value divided by 24 from the factorial times, right here, sine 1 on the RAD mode, 0.3229 plus 0.3229, and finally this term, which will be obviously a positive. Nothing changes between this calculation other than cosine 1, the constant. Pi minus 1 exponent 5 divided by 5 minus the lower limit component divided by 24 times 1 cosine. You're getting here 0.207. That's your plus 0.207. Now all you have to do is add up these numbers and let's see what comes about. We have a 2.643 plus 1.697 plus 0.9688 minus 1.5089 minus 1.5177 right here minus 0.9745 minus this point right here, 0.451 plus 0.702 plus 0.3229 plus 0.207. I'm getting a value here, 2.0886, and I'm putting that down right here, 2.0886. That's the end result of my definite integral procedure, which you can round down to 2. But why are we slightly overestimated? Because of this. Look, I have 1, 2, 3, 4, 5, 6 positive terms. I have 1, 2, 3, 4 negative terms. So I have more adding in, less subtracting in, but I only went to n equals 4. As I go into higher n values, I'll have more negative terms come out, which will bring down that value closer and closer to 2. As you go up to n equals infinity, that value will become 2. But you can see how here the Taylor series has been brought into play. You expand your entire series and then you integrate your entire series by means of a definite integral procedure, which can be tedious, but you can see the U substitution has a lot of shortcuts coming into play because only this component right here is your variable component. Even from here, only the top part is your variable component. The lower part can be pushed out as a constant. This part here keeps staying the same as a U substituent. Everything else remains the same, only the constants change, and the calculation is easy. Thank you for watching this video. Have a good day.